So now we are live. So today we have Patricio Escalona from the University of Santa Maria in Valparaiso, Chile. And today we will talk about bouncy pNGB dark matter via Fermion dark matter. And the time is yours, please. Come over.
Thank you, Jason. So, first of all, let me show my gratitude for your group and your hospitality. I have been very happy this week. So, thank you very much for that. And let's talk about physics. First, I want to talk about some preliminary stuff and then the work itself. Okay, that's the organization of this presentation. So the first important thing to mention is that I do this work with Bastián Díaz. He's a postdoc in the Universidad de Santiago de Chile, or USACH, okay? And he's the dark matter enthusiast that bring me to this field, so I appreciate him very much. And the motivations of the work are the following. First, we have the WIMP miracle, and as Farinaldo says in the last lectures, it's not really a miracle of the weakly interactive particles, but it's a success of the thermal equilibrium hypothesis in the early universe, right? So we ask, what is the scope of this paradigm? Okay, so will we always have Boltzmann suppression followed by a freeze out? Or is it possible to have different kinds of behavior inside the thermal hypothesis? Okay, we ask how far we can go with this thermal paradigm, okay, this equilibrium in the early universe. So for instance, can we have an exponential growth, okay, as in some non-thermal production mechanisms like freezing or the misalignment mechanisms when the dark matter production starts from a negligible abundance and grows up into the final relic abundance that is measured by the Planck satellite, right? Or we ask then, if that can happen, what are the implications for the observables? In particular, I am going to talk about indirect detection observables and signals, okay? So then you ask, okay, the direct detection signal is very restrictive, okay? We haven't seen any signal of direct detection, so the bounds that we can infer are strict and strong. So does that mean that we need to abandon the hypothesis of thermal equilibrium? We don't think so, okay, because we have plenty of mechanisms that can suppress this signal, but can maintain thermal equilibrium hypothesis in the early universe. For instance, the dark matter can be of a Goldstone nature, okay? So the interactions between quarks or nucleons and dark matter are suppressed by momentum, and this momentum or velocity in the present day universe, it's non-relativistic, so the signal is suppressed. We can also have secluded dark sector that has to pass through two portals to reach the interaction with nucleons, or we simply can have leptophilic dark matter that doesn't have interactions with quarks and bypass the detection, and so on and so forth. There are plenty of possibilities. And so, you know, these seminal works of Srednicki or Gondolo or Olive, they start thinking about dark matter candidates in supersymmetric context, right? But they soon realized that the phenomenology of supersymmetric theories is huge, okay? Inside that, supersymmetry must be broken, and the predictive power of these theories is lost, right? So the community move on into effective field theories, okay? But they soon realize that effective field theories can describe the behavior of particles or interactions that have their origins in the ultraviolet regime of energies. So, for instance, light mediators cannot be accommodated straightly into effective field theories in the sense that we put by hand all possible general higher dimension interactions. Okay, so the community move on into what they call simplified models or minimal models. Okay, just to mention a few, singlets as dark matter, electroweak multiplets of the SU2L group, and this family of models have the aim just to explain dark matter phenomenology and not other phenomenology that is empirically saying that we need beyond standard model physics. As far as I know, there are 3 empirical situations that require beyond standard model physics. One is the baryon asymmetry in the universe. Second one is the neutrino oscillations or neutrino masses. And the third one is dark matter. Okay. Okay, dark energy also, but this is outside the scope of standard model, so we don't count that problem here. And you can also have, for instance, theoretical or even statistical problems like hierarchy problem or fine-tuning problems or unification hypotheses. But these are not so phenomenologically well-established signals of new physics, okay? But we like that the big theory that explain all of this stuff also satisfy those theoretical restrictions, right? Okay. So considering the lack of signals, we should study next to minimal models. For instance, we all know the real scalar singlet with C2 symmetry, okay? That is the simplest model you can think of dark matter, in the sense that you include the minimal quantity of fields and the minimum quantity of new parameters and try to explain dark matter phenomenology. But as we all know, direct detection excluded this model a long time ago, right? So we need to be as simpler as possible, but not simpler than that, okay? So again, just to recount the motivations, we have a previous work done and published in the JHEP with Alfonso Cerver in the right and Sebastián Norero in the left, from the Universidad Católica de Chile and Universidad de Santa María in Chile. And in that work, we study a multi-component dark matter composed of a fermion, a Dirac fermion, and a real scalar singlet. We put masses by hand, and we do not have new sources of symmetry breaking. So this scalar singlet doesn't have back-in expectation value. It was a very simple model, and we studied that. We saw that it's viable in some regions of the parameter space. So we get familiar with that kind of stuff. And this work is also done with Bastian, obviously. So with Bastian, we wanted to extend this model. What can we do to give a next step in this exhaustive and systematically search for next to minimal models? Okay. So one thing that occurs to us is to promote the real scalar to a complex scalar, right? And that scalar can acquire a BEV, and the spectrum is richer, and the phenomenology is also more interesting. Okay. So with this in mind, we saw this paper of a New York scientist, and it's called Bones in Dark Matter. Okay, you can find it in the archive. And basically, they say, okay, suppose we have an artificially constructed dark sector with 3 particles. Chi, it's the dark matter particle, and Phi1 and Phi2, and mediators that can be stable or not, and are required to decay before BBN, and so on and so forth. It's very artificial, but they try to explain the chemical process in the early universe and not to explore the scope of a particular model, right? So they say, in the equilibrium phase, everything is in contact with the standard model plasma. So the chemical potentials of everything is 0. And that's pretty standard. And then suppose that the dark sector and the standard model are separated in terms of, are decoupled in terms of this equilibrium, and the chemical potentials start to grow from 0 and to acquire some values in order to describe the correct correct evolution of the abundance, right? And then they say, suppose that, again, these interactions are no longer effective as a contrast with the Hubble expansion, and we have this kind of semi-annihilation on the right, in which the dark matter is in the final state. So we have a relation between the chemical potentials, and as a consequence, the population of Chi particles, dark matter particles, starts to grow. The Phi2 particles starts to feed the population of Chi in that part of the thermal evolution. Okay, so this is exemplified here. So look at the blue line. Okay, so the Chi particle starts in thermal equilibrium, so it is described by an exponential decreasing Maxwell-Boltzmann distribution, and then the dark sector decouples as a whole, so acquires a new chemical potential that makes a difference with the original Maxwell-Boltzmann distribution. And then the semi-annihilations of Phi2 starts to be effective and to feed the population of Chi particles, and we pass from an exponential separation to an exponential growth. Okay? And what about Phi1 and Phi2? Okay, they say these particles are required to decay before BBN, or can be dark matter particles and contribute to the dark matter budget. But they really don't care about what happens in the future of the evolution. They just describe the mechanism and the chemistry of this process. Okay.
But to understand, so why you have exponential drop after 10, where after x equals 10?
Here.
No, see x equals 10. See the line where, yeah, so it was in equilibrium. And then at x equals 10, roughly, you said departs from equilibrium.
Yes.
So why do you still have an exponential drop?
No, I don't get your.
So you're saying that at that point at x equals 10,
the dark sector decouples from the standard model plasma.
So it has a chemical potential.
Yes.
But it still gets the interaction rate did not match the Hubble rate. That's what you're saying.
The annihilations in the left here, those are not.
They don't match yet the Hubble rate.
At first, yes, and then we suppose that those cross sections are small enough to don't be efficient.
No, I know. I'm saying go for the one, right?
Okay.
Yeah, this point here. Okay, comes in equilibrium. And then here.
Yes.
What happens here?
The dark sector decouples from the standard model plasma as a whole.
Okay, and how is the number density evolving with time now, with temperature? Still, both are suppressed?
Yes, but with a chemical potential modification.
Okay, but that's for, okay, now let's say particles, okay, fine. But then, okay, in this period, the annihilation rate does not match the Hubble rate.
No.
Okay, so then it's just suppressed, Boltzmann suppressed with the chemical potential.
Yes.
Okay, mu minus m over t.
Yes.
Okay, fine. Then goes. At what point matches the Hubble rate?
Yes.
Nowhere?
Yes.
Where?
And the, for instance, the x sub b
Here?
vertical line. Yes.
Okay, so the freeze out, let's say, would happen here.
What happened there is that the semi-annihilations in the third phase start to being the only one efficient processes.
The freeze out already
I see.
happened, but then
No, the
after
freeze out never happened for Chi.
The freeze out happens at the end, in X freeze out.
So you're saying, okay, the population of Chi will continue to decrease exponentially,
Yes.
but it doesn't because these guys start producing dark matter particles.
Yes, in the final state.
But why is this exponential?
I will show you some equations in the next slides. Okay.
Because I don't understand why this will give you exponential production.
Exponential growth.
Yeah.
That's why the chemical potential of the Chi particle surpasses the one of all the other particles in the dark sector. So we have the exponential of the masses that are decreasing, obviously, and then we have the exponential of mu Chi minus mu phi 2, for instance. And if mu Chi is greater than the other, the exponential is increasing, and it can beat the other exponential at the left with the masses. I can show you some equations later. So let's just say that, let me just say that there is a parallelism with Big Bang nucleosynthesis. Okay, in Big Bang nucleosynthesis, there is some point in the evolution where the deuterium starts to grow, because there is in the final state of this kind of processes. Okay, so here in the red line, we have an exponential growth of deuterium, and the process is somewhat similar to what what I described just in the previous slide. Okay, so with that in mind, with Bastian, we wonder, what if the particle that feed the bouncing is itself a dark matter candidate? Okay, so that can opens possibilities to indirect detection, because the same semi-annihilation that fits the Chi particle can give rise to gamma ray boxes, for instance. And let me show you this. I didn't talk about the plot on the right. So as the annihilations are no longer the drivers of the relic density setup, we have some freedom. We, how to say this? The annihilation of dark matter particles is not constrained by the relic abundance. Okay, so it can be larger. That's what they are trying to explain in this plot. So here we have the canonical thermal target for cross sections, and the red line represents the signals of this setup in the left. Okay, so it can grow up to 1 or 2 orders of magnitude with respect to the vanilla annihilation driven freeze out. Okay.
This is more correction from today. That's not thermal sigma V.
Sorry, can you repeat?
There's more correction from today's lecture. That's not thermal sigma V.
Yes, you're right. You're right. Yes, it's just sigma V, not thermal average. Yes.
Do you see how?
Okay, so let me talk you about the particular model that we explore. So the exotic fields are going to be a direct fermion psi and a complex scalar S, but gauge singlets. Okay, so pretty simple, right? So we impose a vector and axial approximate symmetry. Approximate in the sense that we are going to break that symmetry softly with these terms in the equation 5. So the Gubi-Goston boson is now going to acquire a mass, and it's going to be a pseudo-Goston boson, and in the kinematically allowed region, it's going to be stable also, and we can have a two-component dark matter model. Okay, so let's look at the Lagrangian. We have kinetic terms. This is standard, and we have Yukawa couplings between the fermion and the scalar field. And we have a potential. The potential includes the Higgs doublet of the standard model, that's H. And we have a mixing that is allowed by the symmetries, right? That will mix the Higgs boson with a Higgs-like boson. We call it a Higgs partner, or an H2, okay? And these Yukawa couplings can be considered real because of field transformations, but this is an extra hypothesis, okay? So the model conserves CP because we impose it, but that is not a requirement of this construction, okay? So you have a question? Okay. So I know this is somewhat messy, but stay with me. The equation 6 represents the stationary point conditions of the potential, and these mu parameters squared, if they are negative, triggers a spontaneous symmetry breaking, right, of the axial symmetry. So we expand the scalar field in terms of these Cartesian components, real and imaginary part, and then we shift the real part to expand the theory around the correct minimum, right? That's pretty standard. And at the end of the day, the Lagrangian that is important to us is this. So we have a mass term, spontaneously symmetry breaking generated mass term for the Dirac fermion. We have a scalar Yukawa coupling with S, pseudo-scalar coupling with lowercase s, with little s, and a pseudo-scalar interaction, Yukawa interaction with the chi, the imaginary part. So remember, chi is a dark matter particle, and psi is also a dark matter particle. And the potential, well, it's written in terms of these fields, and it's very messy. I don't want to show you that. And the mixing angle between the Higgs boson of the standard model and the new Higgs boson satisfy this, traditional equation. Yes. At the end of the day, we have 3 new particles in the infrared spectrum. Okay, after spontaneous symmetry breaking, the Dirac fermion with that mass generated by spontaneous symmetry breaking, and well, H1 and H2, and we identify H1 with the Higgs boson of the standard model with its correct mass, okay, its correct back expectation value. And in terms of the mass eigenstates, the Lagrangian looks like this, okay? So the potential is written again in terms of the rotation of the old fields, and you have a pseudo-scalar Yukawa interaction and scalar interactions with the Higgs-like particles. And the independent parameters that we use for our analysis are 5: 3 masses and 2 couplings. The Yukawa coupling and the mixing, okay? The mixing angle. So you see here, this term here allows for the decay of chi particles into fermions. So if we...
So chi is a scalar.
Yes.
Yes.
Okay, could we go back one slide?
Is the imaginary part of the scalar field here.
Okay.
And as I say, if we kinematically don't allow this decay, chi, a pseudo-Gaussian boson is a stable particle, and we have two dark matter components.
Yeah, so
Yes.
in this case, S, the little s, I mean the S singlet will break softly the symmetry, and then it will develop a kind of vacuum expectation value.
The soft term
Yeah.
is required.
No,
Okay.
I see. No, the value of the S.
Yes.
Okay.
Yes.
Okay, I got it.
So the soft term is needed to give mass to the otherwise massless Gaussian boson.
Yes, you are supposing that the mass of the S is larger than the chi,
The mass of the S.
the little s.
Actually, the little s is not a mass eigenstate. We have H1 and H2.
Okay.
And the mass of the H2 is free. Completely free.
Go back again, just.
Okay.
Wait.
Yes, you mean psi to be a dark matter, and
Yes.
psi to be a dark matter.
Yes.
Yes, I know, but that's because. Go back again. Just
Oh, okay.
Because to me, it's like what breaks the symmetry is the soft term,
Yes.
right?
And the vacuum expectation value
Together.
also.
Okay. So why were you introduced? Why? I mean, you could, for example, break the symmetry just using the vacuum expectation value, right?
Yes, I can do that.
Why are you introducing the soft term?
Um,
And you could also have, even if you break the symmetry just using the vacuum expectation value, you could have, for example, a pseudo-scalar dark matter.
no, you can't because of the Gaussian theorem that says, okay, you are breaking one generator and there are two
that's true.
U1s, so
Okay.
you have a massless particle.
You
But
could have just if this scalar doesn't develop a value. So you could have.
Yes, I
that's
can
true.
have.
One thing, so U1B and U1A are global symmetries.
Right. Yes.
So if they're global symmetries, then I can write this operator side by side. You are now side by global, right? So as, but I can write an effective operator that makes dark matter unstable.
You mean the chi, the pseudo boson?
Either one.
I'm not so sure.
Yeah, it's the global symmetry. I can always do this. Let me see. Let me tell you which one. S side bar S. I have S transforms that way. So I can have So I can have S is given as a chi, right?
Chi is the side is the Fermion.
No, but this capital S
Is the complex field.
goes into S and is the so I can write it S.
No, you can't.
S. No, it's this one. S. Okay, I'll see it.
You mean you call it
In higher dimension.
higher dimension. Okay.
Because there's one thing, Patricio, is that every time you stabilize a particle via a global symmetry, I can always, as global symmetries are not expected to be preserved at a Planck scale,
Of course.
I can write down Planck effect operators which induce the decay of the dark matter particle.
But in this case, that would be a dimension 6 operator, right?
Well, it depends on your model.
Well, if that is the case, it is also cosmologically stable. Not completely stable, but cosmologically, yes.
Not necessarily, depends on the mass.
Okay. And
Even-
for
even if
electroweak scale masses, that should work, right?
Not necessarily.
Okay. I saw your point.
Not necessarily. So, despite being Planck mass, a Planck mass is not large enough to induce this thing, because it's proportional to the mass. If it's a fermion, the decay rate is proportional to the mass of the fermion to the third power. The lifetime is inversely proportional to the mass of the fermion to the third power. So I'm thinking of light dark matter particles, okay, will be stable. But if you consider heavy dark matter particles, the lifetime will be small.
Mhm.
You see? So if you consider heavy dark matter particles, above like hundreds of GeV, TeV, you might be excluded even having a Planck suppression.
I see.
If it's the sixth power, maybe it's stable, but it's a 5-dimensional operator, then it probably won't.
Yes.
It's good. All right.
Yes, I see.
So I have to think what kind of effective operator I could write down. Because have two symmetries, then maybe it's a higher dimensional operator. Okay. But
I should mention that a C2 symmetry is preserved. I mean, with the
it's okay. But if you
even
start with a Z2,
sorry.
you have to start from the very beginning with a Z2.
Yes.
Not break after breaking U1, you generate a Z2. That doesn't suffice.
Okay. But again, this argument has to do with the no-hair theorem, right?
Yes.
Okay. So you said that it's not so strong as we
Yeah, I know,
can
it's
we can
something
we
that
can
it's
wish.
it's not gonna throw your paper away, throw in the trash, but it's something that
You can think about.
yes, someone might raise, hey, but you're using a global symmetry. How
Yes.
can you justify that? And then
Okay.
you can say, well, I can justify saying that I don't care about the head theorem, not perhaps the proper answer. Or say, no, I have computed and I realized that it's a dimension 6 operator that only needs
So at worst, it would put extra constraints in the masses,
exactly.
in the
But
masses.
point is, if the constraint is imposing a dark matter mass to be lighter than 1 GeV, then the whole work is gone.
Yes, I see your point.
But somehow it would be not a problem at all, like to these energies, to some energy scale.
No, because he's worried about CTA bound. CTA is for
Okay, I
masses
see.
way higher.
Okay,
you know?
okay. Yes.
Okay, so
Go ahead.
That's his region of interest.
Okay, I see.
what I was saying, okay, the spectrum is 3 particles. Okay, I just said that, and in a kinematically suitable region, we have 2 dark matter candidates stable, with some caveats from no-hair theorem. Okay, right. Okay, so here you can see the relevant diagrams for the Boltzmann equation solution. Okay, and the important thing here are those diagrams that are contributing to semi-annihilation. For instance, this one here, which have a chi particle in the final state, or his one here that can contribute also, or this one here to contribute to semi-annihilation, and we will see that those are the important processes. Okay, so here are the Boltzmann equations. You see there are a set of 2 coupled Boltzmann equations with the standard terms of annihilation of psi particles into standard model, and we have dark matter conversions also. So as a contrast of the work of the bouncing dark matter that I presented some slides ago, here we try to study the bouncing mechanism in a complete model, considering all the details of the processes and so on and so forth. So we are not artificially saying, okay, let's consider that semi-annihilation is no longer effective, and then this other. No, the model itself has its own behavior, you see? And we have conversions, we have annihilations, we have semi-annihilations here into the two Higgses. And for the other field, the pseudo-Goldstone, we also have annihilations, conversions. So this is the same term but with a different sign. And look here. Here are some not as important but also interesting, like co-semi-annihilation, if you want. I mean, we have two different kinds of dark matter particles in the initial state and one in the final state. So these are the Boltzmann equations that we have to solve. And these coefficients are obviously the thermal average cross sections of the relevant processes, multiplied by the entropy divided by the Hubble rate in a radiation dominated universe, and with the temperature here. Okay. So we implement the model through Langhead into micromegas, and we use that to solve the equation. So just for a comparative context, okay, we call the hierarchies of the two dark matter particles as normal and inverse. Okay, we just call like the normal hierarchy is when the psi is heavier than, and in this case we just have a simple freeze out of two dark matter particles. So they are Boltzmann suppressed until the Hubble rate is more prominent than the annihilation rate, and the two particles just freeze out. And the dashed line is the pseudo-Goldstone, the chi abundance, and the continuous line is the fermion abundance. So as the fermion is heavier than the chi, it is more Boltzmann suppressed. Okay, so that's why it's lower. Okay, and this is any surprise. This is just standard stuff. Okay, just to compare with the next result. And note the mass hierarchy here. We have mass of the fermion 200 GeVs, the mass of the pseudo-Goldstone 150 GeVs. So as a contrast, in the inverse hierarchy, when the Dirac fermion is lighter, we have bouncing of the pseudo-Goldstone. Okay, and you can see that it depends strongly on the mass of the second Higgs. Okay, that's why. Sorry, that's because the semi-annihilations are more or less endothermic. Okay, they need more or less thermal support to be effective. So as the Higgs 2 is lighter, the semi-annihilation is more efficient, and the bouncing it's stronger. Okay, you can see the abundance of the pseudo-Goldstone particle again as the dashed lines, and here you can see some wiggles, and that's because the influence on the other processes also. Okay.
So now I have a more technical question.
Yes.
How did you include the fact that the chemical potential of chi is different from zero?
We do not include by hand, but we check after the calculation, solving in terms of the yields. I will show you right away. Okay, so we have bounds. Okay, okay, and here's a brief explanation of this evolution in terms of chemical potentials. Okay, so at early times, the equilibrium phase via annihilations just imposed that everything is in contact with the photon plasma and the chemical potential vanishes of all species. Then, in later times, the annihilations are no longer effective, and that's a fact of the model. I mean, we do not impose that by hand. It's just what the rates are and the cross sections are. So In that case, the dark matter particles start to develop chemical potentials. Okay, so this is the equation of the co-moving density. How to say this? The co-moving density.
That's the ratio of the moving number.
Yes, but the co-moving density. I mean, it is constant. Is it constant because they are in thermal equilibrium with itself? You see, in the dark sector. So the co-moving density is conserved. Okay, that's conservation of co-moving number density for this species. Okay, that's it. So you can see here in this equilibrium densities, we have Boltzmann suppression in terms of the masses. Okay, that's standard. But the developing of chemical potentials can in fact give an exponential growth, provided that the chemical potential of the bouncing particle, in this case the pseudo-Goldstone, is greater than all the other lighter states in the thermal plasma. You see, so this is what gives rise to the yield. Okay, the bouncing yield.
Okay, that I get it. But and how did you compute this chemical potential?
Aquí, here. If we solve the chemical potentials from the yields, okay, because we know the yields. Okay, the chemical potential, you can think of the chemical potential as a measure of how far of the equilibrium are the distributions, right? So if you compute the chemical potential, you know, taking the logarithm and getting down of the exponential, you can see graphically the situation right here.
Okay.
So, okay.
I know, but the point is the number density is m temperature
Q.
to exponential of minus mu minus m over t. Right? Right? Is it right? Yeah. Right? Is that is m minus mu minus. Yes.
Yes, that is.
Okay. And then, okay, so that's the equilibrium. So the one you have is simply this one. We have exponential minus m over t.
I mean, in equilibrium, it's just with the m, and the actual one is with the mu.
This one.
Yes.
Okay, fine.
So we can compute this using resolving both the equation and making it. And then
Yes,
we can solve for this one. That's what we do.
I see. And how did you do it?
We take the logarithm of the.
So you do it numerically?
Yeah, you
Okay.
can.
Okay.
And
No.
you
You do it analytically and then numerically.
no, just numerically.
Just numerically.
Just numerically.
Okay, so you took the yield multiplied by the entropy,
Yes.
and then you take the log of that,
Yes.
which is how you get the mu.
Yes.
How do you know the mass?
As I know the mass.
Yes.
And how do you know the temperature?
We recover the evolution of the yields completely from micrometers, not just the abundance, the final abundance.
Yes.
We use these.
Okay, you take it at each point what the temperature
Yes,
is.
yes, yes. And you can see
It's
this.
tricky. It's tricky to do this.
You can see that I don't put equal signs. I just put similar because first, when the fermion starts to get non-relativistic, the chemical potential of the fermion and the anti-fermion starts to bifurcate, right? That's standard. So this is one fact that doesn't allow me to put an equal sign. And the other fact is there are other processes. So you have a system of equations for the chemical potentials. Okay, we have equations that are mostly insignificant, okay, but they have a little impact. And you can see graphically here. So here's the same plot that I showed in the previous slide of the yields bouncing. And then we have the developing of chemical potentials. Okay, so in the early stages, they are all close to zero because of equilibrium.
Okay, so that's the thing that maybe we're getting confused.
Okay.
So you have the yield as a function of mu over temperature?
But mu, sorry, that's confusing. Yes, mu is the reduced mass of the system. Yeah, sorry. Yeah.
No,
The
reduced mass, not the chemical potential.
No. But the mu sub chi of sub psi, that refers to the chemical potential. I mean,
Okay.
that we can think of a better notation for that. Yes. See, yeah, I didn't say that. Typically, you take the mass of the dark matter particle here to parameterize this temperature. But as we have two dark matter components, we take the reduced mass of the system. So yeah, I apologize for that. It's confusing, yes. And here is the evolution of chemical potentials and parameterized by the mu reduced mass, right? And you can see in the early stages where everything is in thermal equilibrium, they are close to zero, right? But then start to evolve. And as expected, the chemical potential of the chi particles is more or less twice the chemical potential of the fermion, okay? And the more or less part has to do with what I say, the chemical potential of the fermion and the antifermion bifurcate. And we have other processes contributing to this, conversions, the other kind of semi-annihilations. Okay, so in the paper, actually, we study the behavior of the bouncing in terms of all the 5 parameters that they show, but I don't want to bother you with some algebraic stuff. I just want you to get the physics.
In the right panel is saying that the ratio of the chemical potential should be either 2 or 1, right? So which case is this mu equal 1? The ratio is 1. The solid differs.
No. What I am saying is the chemical potential of the chi particle, the pseudo-Gaussian, has to be more or less twice the fermionic
I know.
one.
And what is this curve?
This curve is the chemical potential of the fermion for different cases. For the same cases that I put in the left in terms of the mass of the Higgs partner.
Okay, and this is what?
The reduced mass of the system. It's just a parameterization.
That because Fernando is asking that because he was expecting that at the end of this curve they would have difference of 2, but he's seeing just the difference of 1.
No, no difference of 2. One is twice of the other.
So it should be the same. Yeah.
So you're dividing chemical potential by reduced mass.
Yes, just for the sake of the presentation. I mean, we read papers and that's the standard way to present it. I mean, it's no particular reason for do that. I mean, we can think just of chemical potential.
I think maybe it is moved the curve.
No, I don't think so because they are all divided by the same quantity. Yes.
Perhaps it
Not a function.
has something to do with the number of particles, since they are related in the exponential. So you can use that. That is larger than it is exponential growth.
Yes.
Yeah.
Looks like it is rescaling.
Yes. Yes.
That's why we are seeing.
Okay. Fine.
Okay. Let's move on. So we ask ourselves, what is the impact of indirect detection signals? In the original bouncing paper, they studied the impact on annihilation of the chi particle, in our case the pseudo-Gaussian, into standard model particles, and that is related to a diffuse spectrum of cosmic rays or photons or whatever, right? In our case, we also will have annihilation into semi-annihilations of dark matter, fermionic dark matter particles, you see? So we can have a correlation between the diffuse spectrum from the pseudo-Gaussian and the gamma ray boxes, for instance, of the fermionic annihilation. You see? So this is a interesting feature of our model. So let me explain this. So we perform a random scan. All of these points satisfy relic density, okay, 100%. In colors, we can see the value of the mixing, okay? So the more red, the more mixed, okay? And we highlight the thermal value of the canonical target for sigma b, right? In the upper row, here and here, there is the normal hierarchy, okay? There is no bouncing. So you can see, at most, you reach the thermal value, as expected. Okay. Okay. And the sigma b is weighted by the relative abundance. Okay, because the dark matter budget is divided between fermion or pseudo-Gaussian. As a contrast, in the inverse hierarchy, when the bouncing is present, we can reach 1 order of magnitude more in both signals. Okay, so that's mainly the result that I wanted to show you. That in the bouncing case, it's represents a 1 order of magnitude enhancement on indirect detection signals. Okay, that's it. And we want to exemplify this in the context of the same model and not with artificial cross sections imposed by hand. You see? Okay. So it is what it is. We have some problems with perturbativity. GIP-psi, the Yukawa coupling, takes the correct value to satisfy relic density in this scan. And in fact, is large. I mean, 10, 5, 1. And if you run the renormalization group equations, that have problems with perturbativity. So that's a limitation of our work. Okay, I think to have in mind. But anyway, let me talk about the other limitation. I think the stronger one. That's the fermionic direct detection. Okay, as I said, the pseudo-Gaussian can bypass direct detection very easily because of the momentum suppression, but the fermion cannot do that thing. So we have two ways to have a big direct detection, and that's in fact like a bad situation to be in, right? So first of all, we have this mixing angle dependence here, and we have this algebraic cancellation between the two Higgses here. So from left to right, I am increasing the Higgs partner mass. Okay, so let's see the right plot first. So we have a big Higgs partner. If we have a big Higgs partner, the direct detection it's big, okay, for any value of the mixing angle, and that's because of this factor over here, right? So in gray or in blue, if you want, we present the direct detection constraint. So everything here is excluded by direct detection, okay? In red or pink, we show collider constraints on the mass and the mixing angle of the second Higgs. Okay, they are coming mainly from direct searches of second Higgses, and electroweak precision tests. Okay, and we plot also. I apologize. I didn't put the legend here. The continuous lines represent the gamma ray box signals. Okay, the cross sections of semi-annihilation of fermionic dark matter. So, to have sizable semi-annihilation and sizable gamma ray box signals, unfortunately, we are in the regime in which direct detection of the fermion is fatal, right? And then here, the second Higgs mass is somewhat lighter, 300 GeV, and this algebraic cancellation is more permissive in terms of direct detection, and we have this sector here not excluded. But again, the gamma ray signals are you know, opaque by the direct detection, and also by collider constraints. And then, if we have nearly degenerate Higgs bosons, this cancellation makes the direct detection insignificant, but we also have these collider constraints. But be careful, the collider constraints are difficult to grasp when you have nearly degenerate Higgs bosons because of the resolution. You see, you cannot distinguish one Higgs boson from another in that case. So you have to take this pink restriction with a grain of salt. But anyway, I would like to mention that even when these big cross sections here that we study in these scans are excluded by direct detection, the bouncing mechanism is still providing enhancement to direct signals. So these semi-annihilations here are still in the ballpark of future experiments, you see. So we would like to see the model, you know, rising above the thermal canonical value, or just the canonical value. But that's not the case. That's not the case. So that's somewhat a limitation of the model. But the concept of the bouncing providing enhancement to indirect detection constraints is still there. Is still there. And let me finish with a comment. I did not put here because of time, but I will mention that our framework comes to rescue the pseudo boson dark matter below half of the Higgs mass. Typically, the invisible Higgs decays and the relic abundance are set by the same mixing angle. But here we have other parameters and the semi-annihilations to drive the relic abundance. So we can surpass the constraints at the same time of the detection of the fermion, relic abundance, and Higgs to invisible decays for pseudo-Gaussian dark matter below, let's say, 50 or 60 GeVs.
So in this case, it would be only for image to nearly the Higgs mass.
Yes, nearly degenerate. Otherwise, direct detection, we already have seen this signal in direct detection, and that's not the case. Yes. So this work is already reviewed by the referees from the Journal of Cosmology and Astrophysics, and they just mentioned minor revisions on the thermalization of the second Higgs because of the tiny values of the mixing angle. Okay, so they ask, and with good reasons, they ask, hey, what about if the H2 lacks thermal contact with the standard model plasma and start to develop a different temperature? What if that happens? Well, we compute and we compare the rates of elastic scattering and decays and inverse decays of the Higgs 2, and we found that to lose thermal equilibrium, we need to have mixing angles of the order of 10 to -7 or -8. So way much smaller than the case that we consider. Okay, so that's a conclusion of my work and of my talk. Thank you for your time.
I have just one question, because you said that the bouncing mechanism can enhance the cross section and then avoid. I mean, can avoid the direct detection. Avoid the upper bounds.
Avoid indirect detection.
Oh, indirect detection.
The way to avoid direct detection is just rely on the pseudo-Boston nature of the candidate.
Oh, I see.
And as I said, the fermion does not have that kind of mechanism, and direct detection bounds are much more restrictive in that case for the fermion.
But in this case, the semi-annihilation processes would help somehow.
No.
No, it does.
Only for the pseudo-scalar.
They are not related directly in that case. Yes.
Okay.
Okay. You have more questions? Okay, thank you very much.
Okay, thank you, Patricio, for the talk. And today we finish here. And so thank you all for being here. Bye.